Check test, check, check test, hello, check, check test, check, check test, hello, check, check test, check test, hello, check, check test.
Plan to.
वंदे मातरम. Good morning. I request you all to rise up for the national song and Tamil Taiwan.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே. வந்தே மாதரம் வந்தே மாதரம் சுஜலாம் சுஃபலாம் மலயஜ ஷீதலாம் சஸ்யஷ்யாமலாம் மாதரம் வந்தே மாதரம் शुभ्रज्योत्स्नां पुलकितयामिनीं फुल्लकुसुमितद्रुमदलशोभिनीं सुहासिनीं सुमधुरभाषिनीं सुखदां वरदां मातरं वन्दे मातरं वन्दे मातरम्.
You may please take your seats. Good morning to all of you. Professor Nilesh Devasa, Director in Charge and Dean IIT Madras. Professor Arul Lakshminarayan, Head Department of Physics, IIT Madras. Professor Bodhraj Mehta, former Head of the Department Physics, IIT Delhi, and currently Vice Chancellor, JIT Noida. Professor Ayodhanath Tiwari from EMPS Zurich. Professor Shanti Iyer from NCAT University, North Carolina, and my colleague, Professor Mahavir Jain, and all distinguished guests, faculty colleagues, students, and participants here. It's really a great day of joy, and I welcome you all with a lot of pride and honor and pleasure to this second international conference on thin films and nanotechnology, knowledge, leadership, and commercialization 2023, ICTN KLC 2023. So we organized the first of this conference series in 2021 as a fully online event. And this conference had originated in part as a tribute to legendary Professor K.L. Chopra, who is widely considered as the pioneer of thin film research in India, in our country. That time in 2021, we were really encouraged with the huge response with the online event, and then we decided to carry forward this with a biennial event. And so this is the first in-person physical event in that series, that is ICTN KLC 2023. When we decided that we had to organize a conference, and Professor Ayodhanath Tiwari was one of the force and inspiration behind all this, then we thought about, and you should be agreeing that now, those who have already arrived in the campus, that what would be a better location than IIT Madras campus to hold such a conference. I'm sure that whatever time you have spent so far in the campus, you have enjoyed every bit of it, and I wish, over next, 3 days and nights, you will have a very good time, other than academics and the talks and the lectures and the interactions and posters, just, enjoy the ambience and the environment. We had more than about 220 abstracts, out of which we have selected 150 abstracts for poster presentations and about 50 for the oral presentations. And there are several, very distinguished guests who have agreed to come from various parts of the world to give the invited and the plenary talks. We are really thankful to you all for agreeing to come over here to give the talk. Many people question the timing of the conference. July, Chennai is known to be not so friendly till about July, August, but it's probably God's grace and otherwise that we are having a relatively much pleasant weather in Chennai, this time of the year, so this year. There were also requests to have the hybrid mode of the conference. However, right from the beginning, we are very clear that we want to give all of you, the delegates, the real interaction experience with the speakers. So actually, we wanted to have all the speakers to give their talk in person, physically in this event. And that has resulted actually a few people who had agreed who could not come here in person. But nevertheless, I am very much hopeful that you will all have a very memorable experience in this ICTN KLC 2023 at IIT Madras. With these few words, I now request Director in Charge Professor Vasa to comment on the event. Sir.
Namaste and good morning to everyone. First of all, this is my first time to be director in charge over here as a student, so I may not be able to perform well, but I'll try to convey my message as a director in charge. First of all, of course, when I was a student, right, and we were also learning about lasers, thin films, etc. We were trying to use lasers and for depositing thin films for lasers to develop some devices based on the laser-based materials. So that was my first exposure in 1990s. But now, today, if I look back, it has grown, right? The thin film area, nanotechnology areas have grown to an extent that what we were thinking about only knowledge at that point of time is now towards commercialization, right? Lots of applications. Of course, very apparent application is solar film, right? Solar films, wide area, thin film fabrication, synthesis, at the same time texturing, structuring, in wide area. It's a challenge, but it has been overcome to a certain extent, and all of you are going to contribute more and more towards overcoming the current challenges and going forward in terms of commercialization, which is really a very important need, considering the material requirement, right? When we go with thin film, certainly the advantages are with the characteristics of the material, at the same time the material saving itself, right, along with the efficiency. So we look forward to lots of good contributions, papers from here, and this conference International Conference on Thin Films and Nanotechnology with knowledge, leadership, where 7 speakers are plenary speakers. So we will be having lots of inputs from the esteemed plenary speakers. At the same time, more than 45 invited speakers, and as I could learn that there are 150 poster presentations. So we will get saturated, right, with all the concepts, ideas, and going forward towards thin film technology, nanotechnology, etc. And coming to our institute, first of all, our institute is having a thin green film all around, okay, as compared to the total size of the world. It's a thin film. And recently, last few days, it is also covered with thin clouds. So it's giving you a great time. It will give you a great time over here, and you will all enjoy this conference. The IIT Madras, as all of you knowing, has been ranked 5 times in row as Institute NIRF, Institute 1 in overall category, as well as 8th time continuously in row as an engineering institute, right, rank 1. But over and above, we are very much proud about our own lots of researchers working here on this campus with many laboratories working towards thin film technology and nanotechnology, and not only the passive applications, but even functional devices, etc. And you will have a lot of good time in terms of even maybe some visits to some of these advanced laboratories, and we will all enjoy your company in terms of research collaboration. So looking forward to all of your interactions, and thank you very much. Once again, welcome to all of you.
I now request Professor Arul Lakshminarayan, Head Department of Physics, to say a few words.
Thank you, Professor Somnath, Professor Vasa, other distinguished colleagues, both on the dais and in the room. It gives me great pleasure, especially on behalf of the Department of Physics, which is majorly involved in the conduct of this conference, to extend all of you a very warm welcome. The International Conference on Thin Films and Nanotechnology, Knowledge, Leadership, Commercialization. As Professor Somnath said, this is one in a series which started in 21, and it seems to be growing exponentially, and it's clearly an area of very wide interest, as Professor Vasa has also mentioned, and has a a large overlap with many of the colleagues, many of my colleagues in the physics department, and I'm glad to see a lot of them here. And the fact that it is also honoring Professor K.L. Chopra, and that's the knowledge, leadership, and commercialization, is clearly a play on words, and I congratulate Somnath for this. Those of you who don't know, his parents, with great foresight, named him semiconducting oxide materials, nanostructure, and tailored heterojunction. That's what Somnath stands for, and that's the name of his lab. So it's fantastic to have all of you here, distinguished researchers in this field, and such an active conference that it promises to be. It's also my duty to say a few words about the Department of Physics itself, which has grown from strength to strength, and so one of the oldest departments in this institute. It now has nearly 60 faculty members who are specialists or experts in various areas of physics. We also have distinguished faculty, international faculty, visiting faculty, and a very active visitor program in which people stay from anywhere between a month and several sabbaticals here. Our Office of Global Engagement is doing a fantastic job in terms of making this possible. To give you an idea of the programs in the Department of Physics, we have 4 basic courses, but degree courses, but of course the flagship one, and which is the most important for our conference, is that of research scholars, and there are more than 230 at the moment on our rolls. So it's a very active PhD program, and we're all thankful to our research scholars for the fantastic job that they're doing. We also have undergraduate program, starting from an undergraduate program in engineering physics, which is a very successful program now. It's a basic 4-year Bachelor of Technology, which includes both the physics and major components of electrical engineering. So we have more than 150 students enrolled in this at this moment. Then we have a 5-year dual degree program in physics, a BS-MS program. And at the moment, about 80 people are involved in this. It concentrates more towards physics itself. Then we have a 2-year Master of Science program, which has been there with us for a very long time, which is very active. Again, we have more than 100 students in this. And then we have a Master of Technology in Functional Materials and Nanotechnology, a 2-year MTech program. Of great relevance to this conference itself. Then we have a very active group of postdoctoral fellows, national postdoctoral fellows, institute postdoctoral fellows, and so on. So it's a very active research environment. Just to mention a bit of the areas in this department, of course, experimental condensed matter physics was and still dominates the research landscape. We have experimental high energy physics, gravitation cosmology, of all of various kinds. We have soft matter physics, we have theoretical condensed matter, many body physics, quantum information, theoretical high energy physics. So we have the entire range, atomic, molecular physics. Just to give you an idea of this as a cross section, the institute, as part of an institute of excellence, investing funds for encouraging high quality research. So we have started what are called centers of excellence, and the institute, the physics department has several of these centers, as well as which have also gone from phase 1 to phase 2. Atomistic modeling, materials design, functional oxides, experimental high energy physics, strings, gravitation, cosmology, quantum information, communication and computing, biosensing, quantum centers in diamond and emerging materials, 2D materials, just to give you a cross-section. This is far from exhaustive. So it's a very active environment, and I'm very happy to be a part of this, and we are separated from this by some distance. I hope that you find time in your busy schedule to come to our department and visit us. Thank you. Have a great time ahead.
I now request Professor Bodhraj Mehta, our guest of honor, to deliver his speech.
Good morning. I think it's a great day for all of us, and first of all, I congratulate Professor Somnath and Mahavir Jain and their students to make a wonderful organization for this, organizing this conference. I know takes a lot of time, and they are already doing very well. Very well. It has started very well. And this is a very important topic, International Conference on Thin Films and Nanotechnology. But I will like to say that for me and for many of my other colleagues, this conference and this morning is less scientific or technical and more emotional and more personal. That's how I feel. Although the technical program will start, and it has which inviters talks and contributory talks and posters and all for people like me and many other students of Professor Chopra who are sitting here, and it's very emotional, personal. And what comes to my mind is that I want to tell you a small story. If you have visited Gangtok, I don't know how many of you have gone, there is a temple there, which is called Babaji, Temple of Babaji, but it's not any temple of any saint. It is a temple made in the memory of a Indian soldier, army man, who got killed in India-China border, and what the belief is that that person is still alive. And it's not a simple temple. There is at the backside is his office and his home, his quarter. And the office, every day they make a new uniform and they keep it there. The salary is paid to this person every year, every month, as if he's alive. Indian Army, they get 2 months leave. He gets 2 months leave, and a ticket is booked for his hometown in the Indian Railway, and his uniform is kept on one seat. If uniform goes, it comes back. They consider him alive, Indian Army. That's the belief. In fact, because it is at India-China border, even the Chinese army people think that they have seen this kind of person on the border. That's this is the strongest, this is the belief they have. And for me and for all of us, I think I feel that in today's, especially this inaugural session, Professor Chopra is here. And he is inspiring us. His life has inspired us. When we are working in Thin Film Lab and Thin Film Group, all of our colleagues, many of them I'm meeting after decades, we got inspired by his life. He was a teacher, but we used to call him Guru, and Guru means that the person who inspires. Teacher is also inspires, but the Guru is, you don't only following his teaching and what he teaches, but you start considering him as your Guru, and that's how we feel. So on behalf of myself and all my colleagues, my friends who are there and who are not here in this auditorium, we pay a sincere gratitude and homage to our Guru, Professor K.L. Chopra. Thank you very much, and I wish this conference a great success. I'm sorry, for us it's a different feeling, and I think many of my colleagues will share my feelings. Thank you very much.
I now request Professor Ayodhanath Tiwari to come.
Good morning, ladies and gentlemen. I'm not prepared for this opening address, but I got emotional, and I would like to ask your forgiveness that we are bringing in the personal, emotional aspects which relates to whatever we are and whatever we stand for, thanks to our Guru. And this Guru is not made only impact on us, but also many other generations of the people who worked or who were related to the lab. And I would like to admire also some of the colleagues here. And personally, I would like to say, Guru is, you can learn from everyone, yeah, including your juniors, younger one. I'm working in the field of solar cells, and thanks to my first project in the lab of thin film laboratory, TFL, thin film lab, that was on spray pyrolysis. And thanks to the work of Professor Santi here today, she used to work on spray pyrolysis, and that was my first project as a, if you're working on the thin films, the first thing you do is cleaning the glass substrate. And that's a good lesson. Throughout of your life, you clean the utensils. So that's what the learning I had. Thank you very much for that pioneering activity. Then first solar cell I made was with Bodhraj Mehta. That was cadmium sulfide, copper sulfide. I do not know whether to appreciate him or blame him. Till today, I'm still making solar cells. And that's now 42 years. And not only myself, but then Satyendra Kumar, who is sitting here, he also joined me. He was almost following me from my college days, and he also got into making solar cells. And I admire Satyendra for 3 words which I see: knowledge, leadership, and commercialization. He is the one who was linked to knowledge. He became professor at IIT Kanpur and then resigned the academic career to take a risky path at that time to become the CTO of a company called Lanco Solar. And this is not a small thing, to take a risk from a very secure job of a professor at a very prestigious place, but also to make an effort to try to commercialize a technology on which you have been working for many years, and you say, okay, this technology is relevant for that, so better you make an effort and prove that. And I think, I do not know about Satyendra, but myself, I also founded a company, and this was all because of the learnings which we had from our guru, Professor Chopra. And he was always saying, do something, do good, and use the science and technology for the benefit of industry, society, be impactful. And even when I used to meet him, he will always say, kuch karke dikhao, kuch karke dikhao. And he was always very inspiring. So I would not get too much into that, but as Bodhraj Mehta said, it's very emotional for us, although he's unfortunately no more here. On 31st July, he will turn 90, and we were hoping when this conference was organized and when the timing came about the organizing, so Somnath took courage to say, okay, that your first conference was easy, but to start something and then follow it up takes some effort. So Somnath and Professor Jain, thank you very much for taking to the second step, and I hope some people who are in the field of thin films, material science and technology, they will continue this tradition. And I would also like to thank the director and head of the department for facilitating the organization of this conference. The campus is beautiful, and also I would like to thank you all for joining this conference and being part of an excellent event which I think would be useful to everyone. Thank you very much.
Professor Shanti.
Hi. Good morning. Namaste. I still get nervous when I stand in front of people, and I can tell you my first experience in TFLI. So in those days, you know, when the way we used to be inducted in TFLI is you had to give 2 seminars in the group. And in the second seminar, I broke down at the end because, you know, after 2 hours of interrogation, it was just, I was in complete in tears. So till I left, I was always teased that whenever Shanti gives a seminar, let's have a bucket, empty bucket. So pardon me that I pay when Dr. Roy mentioned, you know, hey, you may have to speak. I was immediately, wrote some points. So, you know, I was with Guruji in, as we fondly call him, as 1976 to 1981. I was, I think, probably with the third batch, and the third batch of students who graduated under him directly. And the 3 takeaways for me, which stood in my good stead for both my professional and personal journey, was hard work, hard work, hard work. That is topping the list. And then the commitment and tenacity and his mentoring style. So he instilled the discipline and nurtured a tight-knit community culture that promoted intellectual curiosity to be a successful researcher. And for instance, Dr. Chopra, you know, or Guruji as we fondly call him, he was having issues in attracting, retaining female students. So he came up, he said, maybe instead of taking 1 student, if I take 2 students, that may be successful. And that's what he did. I was, myself and another student, Indrajit Kaur, were taken, and we successfully finished after, in a timely manner. I would like to thank all my, TFLites during that time. I would not have completed PhD degree but for their help. They really, I developed actually. They helped me in everything. My co-authors helped me in writing papers. They taught me how to write paper. In the night, they would entertain my dad, who used to be sitting there. They would take me not 1 day or 2 days. They would take me several months. They would take us in the midnight, take us home, actually. And I learned actually learning coffee, good coffee in the, we had to prepare coffee in a few minutes for 40 visitors in very hot coffee. And so I learned a lot. And we used to have a common room where we all used to sit, and we used to have lunch, and we would talk any topic under the sun. And this was, and I remember having a, transistor hiding under the vacuum, listening to the cricket match. So I can go on and on and on. Those are the instances I can never forget. And when I left TFL, I never came back due to my own personal, reasons. And then when I connected again in the last few years, it just connected automatically. It looked like, we've just, met yesterday only. So it was and I had no problem with the next generation TFLites. I feel the same kinship with Dr. Roy and other group. So this speaks volume of Guruji's mentoring style, and in addition to his stellar contribution in thin film technology. And I'm quite confident Guruji legacy will continue through TFHLites for several decades to come. Thank you.
So I now request my colleague Professor Mahavir Jain to give vote of thanks. After that, we will proceed directly towards the first plenary session.
Good morning, everyone. It's my pleasure to give vote of thanks. Of course, the vote of thanks is not in order maybe, but yeah, let me, at the onset, let me thank Director in Charge, Professor Nilesh Jivasa, for sparing valuable time in coming here to inaugurate the conference. And then, of course, our head of the department, Arul Lakshmi Narayan, to give consistent support for whatever we need as such. Then, of course, distinguished guest on the dais, sparing valuable time, particularly the Professor Tiwari and Professor Bodraj Mehta and Professor Santi Iyer, to come here and grace this occasion. We are thankful to various units which is working in the background, particularly engineering unit, horticultures, ICSR staffs, particularly working, supporting the audio, video, and of course, telecasting it on the YouTube as well. My heartfelt thanks to all the sponsors who has sponsorship. I'm not putting their names here as of now. We'll be having the grand thank you in the when we are closing this thing. Then, of course, big thanks to the august audience, without which no event can basically be successful. So I thank you all for sparing your valuable time, particularly, I mean, at this time of the year, July, when it's not the time when you have normally the conferences. You are not prepared for attending the conference at this time of the year. So thank you very much for sparing your valuable time coming here and attending this conference and interacting and creating a good environment. Thank you once and all.
Thank you once again. So we will now have our first plenary session. I request the dignitaries to be seated. And I will now hand over the mic to Professor M.S. Ramachandra Rao, Chair Professor, Department of Physics, who will be chairing the first plenary session. And the plenary talk will be given by Professor Manize Razegi from the Northwestern University, Illinois. Get down.
Okay, very good morning, and it's a great pleasure to be chairing the first talk of this wonderful conference. I've always had a special bonding with Professor Chopra. I'll tell a little small story during my talk on the last day. The first plenary speaker of this 3-day conference is Professor Manize Razegi from the Northwestern University. She's been an extraordinary researcher and scientist for over 4 decades. She's a pioneer in 3-5 semiconductors and optoelectronic devices, mainly working on gallium arsenide and indium phosphide. You should all read her book on the MOCVD challenges, where you'll get to see how she has carried out her research over 4 decades on these very important 3-5 materials, which are very essential for many optoelectronic devices, all the way from mid-UV to near-infrared regions. She has co-authored more than 1,000 papers and authored 34 book chapters and 20 books, including a textbook on MOCVD challenges I mentioned about. She's the computer engineering and director of the Center for Quantum Devices at Northwestern University. She has more than 60 US patents, and she has given more than 100 invited and plenary talks. She has lots of fellowships and awards to her honor. One of that is IBM Faculty Award in 2013, John Chakralski Gold Medal in 2016, and the Benjamin Franklin Medal in Electrical Engineering in 2018. And they've given me a 4-page CV of yours. If I read all of that, you lose your talk time. So I'll stop there, and let's welcome Professor Razegi.
Good morning, everybody. First of all, let me to congratulate Professor Somnath with his wife, Professor. I believe that, I don't know if his name again is Somnath or not, but thanks first though. Now, it's a great pleasure to be here, and always my talk is for young generation. And I'm telling always, past, present, and future Nobel Prize winner. I just had a meeting in Paris last week with 6 Nobel Prize. That one, it was the present one, that Alan Aspect. So, my talk, where is the talk? You have somebody that has to help here, please. Okay, yes, the student has to be much more active, please. Okay, yes, please put the talk up. So, my talk today is for all of the different background, multidisciplinary, and at the same time, is going to be for undergraduate, graduate, and at the same time, the great scientists with the different background. So, yes, could you please, all right. Okay. All right. So, as you can see from the title of the talk, it's the quantum science and technology of semiconductor optoelectronic from deep UV up to terahertz, past, present, and future. Everything that I'm giving to you, that is going to be a small part. You have to know it was, it is, and it's continue to be always the subject of all of the scientists. So I want to tell you, nature has stimulated the human mind and invention before recorded time. So let me to start by my talk has to be introduction. I'm giving you some UV quantum semiconductor device, infrared to terahertz, and at the same time based on lasers and detector. Now we heard some expert at the same time from the solar cells, but you have to know that solar cells is very similar to the light emitting diodes. So the physics behind it the same. And at the same time, the foundation of the science is 3 active component: transistor, emitter, and detection. Lasers, LED, and detectors. I would like to start by a quote from Persian poet Maulana. He wrote, "Look inside the tiniest particle, you will find universe inside." Nature provides us a full assortment of atoms in periodic table. Are the building block of all matter and works hands in hand with their partner, photon, a piece of light, to communicate energy from one atom to another. When nature binds atoms together, the combination provides nature a rich palette of color to decorate the world around us, also giving rise to the functional complexity of nature. The wing of a butterfly, the feather of a peacock, the sheen of a shell are all examples of photonic crystal, nanostructure arrangement of atoms that capture and recast the color of rainbow with iridescent beauty. Each atom then is with the different electronic structure create light with the different color and energy when oscillating from deep UV, from gamma ray, X-ray, ultraviolet, visible, infrared, terahertz, and beyond. But yes, that is much better. Okay, great. Sorry. So, but our eyes can see only a small part of this electromagnetic spectrum, the color of rainbow. So, to see beyond the visible light, scientists have invented artificial eyes, or such as infrared camera. But however, there still exists frontier within invisible light spectrum that we cannot yet detect. To both see ocean light in any wavelength range across the electromagnetic spectrum requires a team of scientists to invent new model, new material, and new devices. So that's what my group at my Center for Quantum Device is dedicated to exploring this frontier of unseen by using the semiconductor, quantum semiconductor, material, physics, devices from deep UV up to terahertz. So, for detecting and creating light in the different spectrum range require first the profound understanding of the structure of atom through quantum mechanics. And as Niels Bohr mentioned, anyone who is not shocked by quantum theory has not understood it. So if we, and some material that called semiconductor, the heart of all modern quantum, electronic, and photonic. So I would like to attract attention of some of you that you are highest level physics professor and you have the background expertise, and some of the new students. Semiconductor today, when we are speaking, any one monolayer of any material is a direct semiconductor. What does mean semiconductor? It means that we have the particle electron can attract the energy and go to the higher energy level, that is detection, and coming back, that is the emission. So that is the semiconductor. So we can see that that is really a start by a single atom. And now you have to understand one thing, what is coming back? The things that we understood and we understand for the moment from the science, physics, quantum mechanics, say that the particle, neutron, proton, all the time moving, and at the same time electron, that the negative charge attracting the energy of this movement that is coming from the vibration of the particle, and that is going to create exactly, as you can see, the light. But I'm asking always in my class from all of the students, what is the basic of life? What does mean if this movement stops? All of you at any level, I would like to think about that. And now coming here, it is well known that silicon in the column 4 is the best semiconductor for electronic material. Why? Because we have two dielectric, silicon oxide, silicon carbide, have exactly perfect lattice match to silicon, and that is the best that we can have. But again, as God create only the perfection for himself or herself, not for there are some problem. What is the problem? The silicon has the diamond crystal structure. It means that no. And at the same time, silicon is indirect energy gap. Excellent covalent bonding, but indirect, so it's not have lasers. Now, if we come to the column 3 and column 5, we say that 3-5 semiconductor. The 3-5 semiconductor, they have covalent bonding, but they have direct energy gap, and most of them, they have zinc band structure. It means that they have the cleavage plane, so it's excellent, we can make lasers with. And on the other hand, by doing these 3-5 semiconductor, by doing the binary, ternary, quaternary alloys, we can find to have lattice matched, and we can do that by atomic and gap engineering to make optoelectronic devices, such as lasers and detectors, from deep UV up to terahertz. That is something, and now that is the things that I would like to explain to all of you, and I am going, again, not because I cannot go very fast for all of you, so I want any of you that you have the question, everything, I would like to encourage you, go to my website, and as you mentioned, is not only 100, I gave more than 1,000 plenary and the invited talk, and that just 2 weeks ago, it was in Arizona, the University of Arizona Tucson, that I gave the distinguished lecture, and the talk they put on the website. So is that on YouTube, and you can have the access. But what is the basic? If now you use what was the most important achievement of the last century, it was 3 things. First, it was the development of the bulk crystal growth, Czochralski, that it was a chemist 100 years ago from Poland, and that when instead of to put the ink, the pen in the ink, he put on the molten zinc, and it was a starting of the crystal growth. So when you have the bulk crystal growth, if you have bulk such as silicon, gallium arsenide, gallium phosphide, anything, unfortunately, if you look the physics, density of a state as function of energy is parabolic. So if you make the device, any device is not going to be very efficient. Now, if you use epitaxy, as I mentioned to you, it was bulk crystal growth. After that, it was epitaxy, liquid phase epitaxy, vapor phase epitaxy, MBE, MOCVD, gas source molecule, the difference, and photolithography. That 3 of them together gave the possibility to go to the nanotechnology. So here, if you have now to use the bulk and to use the quantum mechanics and to do the atomic and gap engineering, make the quantum well, you have the 2-dimensional electron gas, and the density of a state as function of energy, it becomes much better, and you have much better performance of the device. Now, if you use the bulk epitaxy and at the same time photolithography, you can come up with the quantum wire. It means that, wait, yes, here. Okay, you can make the quantum wire, but again, the density of a state as function of energy, as you can see, it means that artificial molecule But if you use, again, the photolithography and to go to the three-dimensional confinement, or quantum dots, or artificial atom, that is the basic at the same time for some of you for the quantum computing or the superposition, all of that you can see, that is the objective. Now, for some of you to understand, especially the young scientists, all of you, the students, to know that who am I? I am the Persian. And I've had started nuclear physics for the neutron activation analysis of and the gamma spectroscopy for the trace element, and my objective was to correlate that with exactly the human health. Because my father was smoking, and they were telling that he's going to have the cancer. So he was telling my uncle, working, he has 90 years old, and no problem. So what is that? So I wanted to find the correlation. But unfortunately, one day I had the dose of the mortal dose of the radioactivity. They stopped me, and I couldn't forbid me to work on that. So I went to the nuclear, the fundamental physics. I did the phase transition in perovskite, that the perovskite that now most of you are working with, and to have the phase transition using the electron spin resonance and the paramagnetic ion, such as gadolinium, europium, and to have the information about the understanding the fundamental, really, of the science. But unfortunately, again, everybody was coming, asking, what's the application? So that it was, after my science doctorate in France at the Orsay, I went to the Central Research Lab of Thomson, that of some of you don't know. At the time, Central Research Lab, it was one of the most prestigious, parallel to the Bell Labs in the United States, that it was in France, and it was famous department of gallium arsenide. So what I did, I would like again to attract the attention of all of the students, the curiosity and passion, and to go. The first things that I did, it was using the 3-5 semiconductor, gallium arsenide, and as you can see, I calculated, and I did this, all of the binary, ternary, quaternaries, with the difference again, wavelength, and that when I did that, again, it was in 1982, and that it was the first to be in color, and this view graph went at least maybe 2 million everywhere that they were doing the study the technology again of the semiconductor, and just this one on that is the second second volume, second edition of this book, because all of the different publisher was asking me to write the book, and that you are going to see that how I did that. This one that you can see here, that is the world first superlattice of indium phosphide gallium indium arsenide. And now, what is the importance? Immediately, when I went to Thomson, they were telling that I didn't know. The student, you have to know that after my science doctorate, I didn't know what is a semiconductor. When they asked me what's a gallium arsenide, I said something like germanium. If I know anything about the reactor, of course, nuclear reactor, but no epitaxy, reactor of the epitaxy. I said I don't know anything, but I know only one thing. If I like something and somebody can do, I can do better. That is the message for all of the students that you are here. So it was, at the time, some of you know, it was the lasers, 1.3, 1.5 micron, and at the same time, the detector, gallium indium arsenide indium phosphide, for telecommunication. Of course, it was 50 years, everybody was working, especially the Japanese, but they were using liquid phase epitaxy. And that, with the liquid phase epitaxy, it was a problem, and it was not impossible. It was impossible to make distributed feedback lasers, or the high power. So I tried to develop emissivity, and I didn't know, again, for the student, I didn't know what that means. But I had the background. So immediately, I tried to find the way and that it was the reactor I developed, and that many different the publisher, they asked to have that, and I make this book is the first volume of the MOCVD challenge. I put that, and I did it in 1 week, and that exactly is very important for any group that they are working with the 3.5. So, but after that, what happens, again, that look at here, that it was the first distributed feedback lasers that make the price of the distributed feedback laser 1.3, 1.5 micron, it was more than $100,000. Nobody can find it, and that now is more than less than 100. And now I did on silicon substrate. That is again, the silicon substrate, the way that I did, again with the theory, the quality was so good that they were telling that is good because it's on silicon. That is actually when 89, and now today, as you know, the objective of all of the different great group in the world is how to make the laser on silicon. All right? So, and that what happens, it was, again, now pump lasers for the telecom, 808, 980, gallium arsenide, and they were doing, again, with gallium arsenide, gallium aluminum arsenide, and with molecular beam epitaxy. That, again, has a lot of problem. So what I did, again, I developed and took the patent for the aluminum-free. It means that using the 3.5, and I published immediately in Nature, and that is changed, revolutionized the technology of high power pump lasers. And as you can see here, that it was again the subject of my second book, and that it was from that I had the exploratory material labs at Thompson, and for information, it was the first time at Thompson Central Research Lab, it was a women to be there and at the same time to be head of the lab. And that I had, everybody was coming to sign my gold book, and here you have my first PhD student, Dr. Olivier Horiba, that you can see is the director of the innovation of Horiba that support this meeting. The Dr. Martin Dufour, that he is the vice president of Thales, that he's again in, and that is my daughter, that she is the CEO of the Nanotechnology in Paris. So everywhere they wanted me, and most important part, that it was MOCVD conference in Japan, 1988, and I was the first plenary for the Japanese group at the time. And as you can see here, they put that Razegi outlined sheer diversity and potential of MOVPE with the catalog of first new material, highest mobilities, sharpest interface, and new devices. One delegate described Dr. Razegi as a Madonna of MOVPE in her growth. South of Paris producing material miracle, while another referred to this type of work as the essential driving force behind. So we heard about all of you how the material is important, how the nanotechnology is important, and you can see, because before it was not very prestigious. For me, when I was doing my PhD and my science doctorate, this engineer, they were preparing the material for me. But after when I started, it becomes important, because now all of the scientists and the great, especially the physicists, they are to understand the importance of that. So what happens, it was everywhere. They wanted to have me anywhere in the world, and they were coming, but it was at Northwestern that they sent, the dean came 2 times in Paris, and they were that only, I believe that only Professor Ayer knows that, because you were at at Northwestern to see because just on the Michigan Lake, they were building again they were building a filling of the lake, and they building just on the lake here, and that is here, and that I started by a scratch, and it was interesting because they put that in the daily of Northwestern, it's probably our highest biggest hire in 20 years. The offer, it still is unique. But what I did, I started by scratch. I built the facility that I knew what I need for this kind of nanotechnology that we are speaking about. And that I make a center for quantum device at the time, and to put that is a multidisciplinary, because this kind of nanotechnology that we are speaking is multidisciplinary, is the physics, chemistry, material science, everything, bio. And I put that now from the theory, material, fabricate growth. For each material, you need a special reactor design, not only MOCVD, not only MBE, so has to be, again, according to the material and the need, all of the characterization, optical, electrical, structural. More you have, more is important, because with the semiconductor, it's so complicated. You are dealing with atom by atom. So, and after that, all of the processing, exactly, because you need very sophisticated facility in order to be sure that you can do the atomic, again, engineering, and that with the device, and exactly, and everything that you can see here, they are the first, and first it is, and it's continue to be again a day. And that I inaugurated in June 6th with Lewezaki and von Klitzing. And as you can see here, I didn't have time even to change. All right. So what happens here is important to listen, because, all right, yes. Not working. It was working before. You can come. Okay. Yeah. Put that here. Mm-hmm. Say, boy, you put that here. Here. No, yes. Yeah. Open. Okay. That's it. Matter is working. But it was the meeting that we had, and it was the Kumar Patel, the director of the. Yes, that is not, unfortunately, you can. It was working before. Okay. It's not important, but you can see that it was Kumar Patel, the director of the Bell Labs. Some of you there, you have to know that who he is, exactly, that he's coming. He came and he gave a talk, and he said that, okay, I came only to say to Professor Azigi that I'm not against her, that she didn't come to Bell Labs. And to say that, yes, his talk was 40 minutes, 30 minutes, and not 20 minutes that is going to. So now I would like to exactly to come to have to say that not only I created the center, but I created very strong educational basis at Northwestern. The curriculum of the undergraduate and graduate. And I created for the textbook that this one of the book that is not here, that I developed the 2012 with Lewezaki and von Klitzing, the wonder of nanotechnology. That this book is at SPIE, and it still is one of the most important book. I believe that your paper and your picture at the same time is in this book. And but here, one thing that is very important is my new book about the wonder, that is the mystery of carbon, the introduction to the carbon atom. I didn't speak for you, but you have to understand. Carbon is one of the unique materials in the periodic table and in the nature that we had already 2-3 Nobel Prize buckyball, Nobel Prize for the graphene, and that is not finished. It's a lot, but again, is indirect gap, but that's the future, and that this book I would like again that to have is going to be very, very important for the future. So now I would like, and to see that the fundamental of solid-state engineering 4th edition just came out to 2019, and as you can see, more than 2 million copies went out, and that has everything that you want that is necessary to understand really nanotechnology. All right, so now let me to say that what we are doing. We are doing the mainly T5 semiconductor for not only transistor, but all of the optoelectronic lasers and detector, from deep UV up to terahertz. Now, I would like to start with the UV part. Why? For all of you, you have to know that on Earth, the atmospheric ozone attenuates the wavelength less than 290 nanometer. So we have a solar band window between 240 to 290 nanometer. So the optoelectronic device, it means that we have that is opaque. So the optoelectronic device for the UV are crucial for space and on the Earth. But the most important part, the UV light deactivates the DNA of the virus, bacteria, pathogen, and destroy their ability to multiply and create disease. On the other hand, most of the biological agents, such as coronavirus, the anthrax, tyrosine, when we excite them with UV light, they have the fluorescence. So if we have the detection at the same time, we can have very simple device to detect and identify this kind of harmful biological agents. But at the same time, we need more and more the deep UV part, and I'm going to explain to you later on for the terahertz at the same time. So what is here, what you can do is with the, again, colon 3, colon 5, 3, 5 semiconductor, that most of you, I'm sure that you are working on that, and to use again, we can have from deep UV and come by the atomic gap engineering to go and to have up to the infrared and even the terahertz. But here, that is the part of the solar band. But aluminum nitride, gallium nitride, we cannot have bulk crystal growth for it. And you are going to see later on what's the solution that I'm giving you. And that, so that again, when I went to Northwestern, I had a call from the agencies because everybody wanted to give me the, and they said, can you do the aluminum nitride P-type? So I started by that. I built this reactor with the Extron. That Extron is the, again, German group. And that, it was exactly by using sapphire substrate. Because sapphire, you can have excellent material and is the, but has the Wurtzite structure similar to the gallium nitride, aluminum nitride, gallium nitride with the material. So that here, by using this sapphire and doing atomic gap engineering, as you can see here, to make, first of all, the material P-top with the P-top of the aluminum gallium nitride, that's my patent. But unfortunately, it was too early. Northwestern couldn't even understand. They didn't pay for continuation. And then, and at the same time, you saw that later on, we had the Nobel Prize, Nakamura, and the Okazaki for the blue lasers. But blue laser, they did gallium nitride, gallium indium nitride. But aluminium nitride, gallium aluminium nitride, all of that is developed in my group. And exactly as you can see, for example, Daniel Walker, one of my students, that she was doing that. She is now the vice president of Global GE. And that, not only we did exactly, as you can see, that is the responsibility as function of the way 4, 5, 6 order of magnitude, the rejection ratio, and that is the limit of the theory for the quantum efficiency for the PIN, the 1, and as you can see, that's the reason I mentioned to past, present, and future. So that is the results at the present time. Everybody working and is going to continue. How long is going to take to have to repeat the similar result? But we did another thing. The silicon, because silicon, you can have very large area, 15. And everything we would like to put on silicon. Why? Because the mechanically is very strong at the same time. So silicon, the VLSI and PIC, photonic integrated, so everything we would like. And so what I did, we did the development of the lateral epitaxial overgrowth of aluminium nitride on silicon. And just on top of that, that it becomes perfect material with matchless dislocation. So I would like you to look at here, that if you have a molecule of anthrax, if you shine with the 280 nanometer, immediately you can have the fluorescence, and if you have the detector, you can detect that it was all of the biological and chemical sensing worked best in all of that we did when 2003. So what happens? For the coronavirus, as you can see here, the Nishio, Japanese, and the Seoul, the Korean, they try to demonstrate with the LED of 280 nanometer, you can kill coronavirus more than 99% in 1 second just on the surfaces and in the air that we breathe. And at the same time, to do exactly as I showed you for the detector and laser that we have, we can demonstrate again with the, again to have the system that can detect and identify that. Now, that it was the first lasers, blue lasers, came in Nishio, 1993, that it was Nakamura, that when he was there. The second in the world came from my group. Again, as you can see here, that is the excellent it was, and nobody could believe. So the Bell Labs called and to say that if you are giving to us, we give to Nakamura to review, and they did that and it's published, say that, okay, that it was. Now, something that is important, as I mentioned, deep UV, single photon detector, avalanche photodetector, Geiger mode are very, very important application. So that is just our new result, and with one of my genius students from at the same time from from India, Lakshya Gautam, and just before I come, the MIT Lincoln Lab asked that they need, and they asked to have our detector to measure, and that's the future again, the results, the future activity, as I mentioned. And that, again, that is another result for the low dark current UV aluminium gallium nitride on aluminium nitride substrate. But what's the problem here? The problem is the following. With the aluminium nitride, we cannot go less than 200 nanometer. But as I explained to you, we need for less than that. Why? Because all of the virus, the difference that is coming every day, we have the LED and detector in order to be able to detect them. So now, what is the solution? I would like to attract the attention of all of you, because that is the kind of, to give the ideas for the future research, is the gallium oxide, because that some of you are working, and especially Professor Somnath, his wife, they are working at the same time on the oxide. You have to know what is the gallium oxide. is a perovskite and is the polymorph, it means that when you have the oxide that the symmetry, crystal symmetry is low, you have the phase transition. And that, by doing the atomic and gap engineering of this material, there is a possibility to go further. And on the other hand, with gallium oxide, we can have the substrate. We can make the Czochralski substrate, and is the direct energy gap, and 5 electron volt, that is the energy gap. So that you can see. So what is the problem here? Again, that is one of the subjects that my daughter, that is the pioneering that they were doing. So from the NSF, they called me and they asked me if I can do this material with MOCVD, because that is very important. Look at that here. The beta phase is the monoclinic and has the Baliga parameter. That is very important for the transistor. Is much higher in this material by comparison to the gallium nitride, silicon carbide, so that it becomes the important for the high power transistor. And that at the same time, at the present time, you have to know that that is the multi-billion on that for the high power transistor. And one of the most important things that you have to know is very radiative hardness. It means that by comparison to all of the others, they showed that is the very, very important for the future. So that is that. No, and at the same time, the beta copper phase has some more important information. So, and that is the, again, what happens that when they ask me, with this material similar to aluminum nitride, we cannot make the p-top, so we make the p-top by using the silicon as an amphoteric that is published. I have the patent, and that is just, we demonstrated the phase transition of the copper and beta, and it's just on the cover of the journal, and that is coming. So I'm not going to the detail, only I will tell you that we demonstrated the transistor fin FET with the p-top at the same time. That is published, this result. So now, heterogeneous, because we tried now with the nanotechnology to come and to put the advantages of the different material together. So here we did, because that is the physics again. If you put the nitrogen polar of the aluminum nitride, gallium aluminum nitride, with the beta gallium oxide, you can have two-dimensional electron gas with the very high mobility. So that is the first demonstration we did. Here we have the sapphire substrate, and at the same time to put the gallium oxide on top of that, that is we demonstrated very high mobility, and the opposite to put that no gallium oxide on aluminum gallium nitride, that is the X-ray, and as you can see here, and the mobility, everything. So I would like now to go to say that from the first day that we started aluminum nitride, we demonstrated one after each other everything, and everything is applied physics letters. Why? Because when I was asking from all of my the supporters in the government, they were telling that applied physics letter journal. So that's the reason, and everything that you can see is there. So it was, it is, and it's continue. That is that. Now let me to change now to go to the infrared. Infrared part, there are two parts. Lasers and detector. And I'm going to, how much time I have? Okay, only 7 minutes. Sorry. You took a lot of my time for the introduction, so please forget it. Okay, follow me. So you are going to have two parts. One part is the lasers, on the other hand, detector. And my objective is the following, to give you again a flavor and a kind of inspiration and the subject when we are speaking about nanotechnology, why is it important and how much you have to make it really seriously. So coming to the laser part, for the semiconductor laser diode, from the deep UV up to terahertz, using the 3.5 semiconductor, everything that you can see, I demonstrated, I showed you about the 890, that's my patent, and at the same time, the license and that, and everything is in the MOCVD Challenge Volume 2. For the 1.3, 1.5, everything is in the MOCVD Challenge Volume 1. But I encourage, because some of my genius postdoc Chinese, because the Chinese, they try to pay a lot and to have the best Chinese that they are outside of the country, and especially they need everybody that they are in my group. And not that Dr. Fei Hu, that he did his PhD in École Normale with a lot of Nobel Prize and 3 years in my group. He went there to Beijing. The first thing that he did, he bought the Emissivity Challenge. And I encourage you to read that. Any material that you are doing is not only indiophosphate, it's not only gallium arsenide, to show you how to do the science and research in nanotechnology. So that this book that you can see is going to be in 30, 40, 50 years, when I'm not more in this world, it still is going to be a kind of reference. So now for the indium 35 micron antimonide-based interband, because you can have two kinds of laser, interband or intersubband. Interband, you have here, if I show, first of all, application, all of you, especially the young, then you do something. The first objective has to be why. Opposite to the talk that the one of you that you mentioned thinks about the money, how you can make it. No, how you can solve the human problem, not to make money, not to put the production. As a scientist, you have another very important role of to finding the problem. As you can see, your president, he passed away for the coronavirus. That is shame on all of us as a scientist to say that what we have to do in order to solve the problem with the virus. So now here, for the lasers, you have or interband or you have intersubband. Interband, it means that you have the electron and hole and active layers semiconductor, and you do electrically injection or the optically. So the electron is go to the electron and hole in the conduction and valence band, they come together and to combine and to give the laser. And the wavelength of the laser, it depends on the energy gap of the semiconductor. Then you go to the infrared. This energy gap, it becomes very small. So you cannot more because it becomes like a KT. So we go to the intersubband. And what's the origin? It was first Lewezaki Nobel Prize gave the ideas of the superlatives after 100 years from the exactly quantum mechanics. And that the Kazarinov and Suri, they gave the ideas of intersubband to make the lasers. And that, for that, after that, became the group of the Bell Labs, the Federico Capasso, and my group at Northwestern, at DARPA, Ellen Durvasula, and the Henry Everett from the Army, they came and they gave the condition for my group to do interband 35 and Federico Capasso's for the intersubband. And that, after 3 years, they did the first demonstration of the electrically injection of the quantum cascade, the intersubband, and they put the name quantum cascade laser. And that after that, 1997, 3 years later, the DARPA came to me and they asked me, my group, to be involved. So what is the quantum cascade lasers for all of you, the students especially? That is here is a kind of intersubband, superlatives, and how. Here you have this comb shape is the alternative conduction band, the energy of the different semiconductor. The horizontal way is the distance. The vertical is the energy. The Wiegand curve, they are the calculation, theoretical calculation of the wave function. And the height is the eigen energy. We have, for each section, we have active layers and we have injector. The active layers is responsible for the lasers, the electron, and that the reason that is that because it's the unipolar and it's a conduction band, so we are under the electric field. So the electron come from the upper level to the lower level, and is create photon. And this photon, and the role of the injector is to collect the used electron and here and to reinject to the next stage. So each stage we can repeat many times, and each photon can create multi-photon. So as you can see, that is the structure of the quantum cascade laser. So you need now to do some simulation. That all of the undergraduate, you can do that. And for the simulation, we do the electrical simulation. Why? To determine which material we are using, the composition, the doping, the thickness, and all of that. And we are using the Schrödinger equation. And we do the optical simulation. The objective is to decrease the loss. And for that, we are using the Helmholtz equation. And for the thermal, again, objective, we do the simulation objective to increase the thermal conductivity, and we use the thermal equation. All of this equation is the second order, again, differential equation, that as the structure is very complicated, we have more than 2,000-3,000 layers, so we can use it numerically. But it's not the calculation that is important, because anybody can do, but the important is to understand the physics behind of that, and to understand, again, nanotechnology, to understand atom by atom how you can control. And here, exactly, what I did in my group, we use, again, the element of the colon 3, colon 5, 3, 5 semiconductor indium phosphide based quaternary, ternary, exactly as you can see, and you can do at the same time really to change the composition and to have the lattice match, everything. But here is I use now, because that at Bell Lab, everybody was working using molecular beam epitaxy. That is not good for the indium phosphide base. So what I did when I went to Northwestern, I developed gas source molecular beam epitaxy. It means that I combine the MOCVD and MBE advantages to put that together, and that to use here. And that is the typical structure of the quantum cascade. Here you have a digital camera of the one packet quantum cascade. Everything that and that is 1 centimeter. Everything that you can see, that's the heat sink copper that I developed 40 years ago at Thomson for the laser 1.3, 1.5 micron. The quantum cascade is the small things that you can see here. And if now I zoom, SEM and here in this box, you have the wire bonding on the diode, Here you have the double channel that I'm doing, and in the middle is the exactly active layers. In this structure, I have 30 period, and active layers is 1.35 micron. The active here, as you can see, is a 30 period of the difference structure that you can see. Now, if I can come here with the transmission electron microscope, each layer has a few from 2, 3 monolayers up to the 5, 10 with the difference composition, and that is the structure that you can see. And now I can show you immediately what happens, that it was March 29 that they came in my office and they said that when you are going to do quantum cascade lasers, I said that by end of the month, end of the April. Why? Because I have the reactor that I was doing this material for the detector, for the QUIP, quantum well infrared photodetector. So it was easy immediately to put that and to come to the structure of the lasers. And I had all of the activity for the volume 1, volume 2 of MOCVD challenge. It was everything for how to make the laser. And that, exactly as you can see in the photonic 1997, it was the world first, again, to mention. And during 10 years, 5 years, my group was only one to have continuous wave high power in the world. if I didn't publish, if I didn't give the information, the result, everything, it was impossible. Anybody can come even nearby. But today, as you can see here, my group is only one to demonstrate it. Continuous wave operation from 3 to 12 micron. And that to have watt level and to have the record of the 5.7 watts with the quantum efficiency in continuous wave 22% near 4.7 micron, that is very important, and the record continuous wave 8.2 watts at 8.3 micron. And this result, you have to know that some of that is published in 2010, 2011, and it still is, the record still is unique, and it's going to take maybe 10, 20 years if any other group can come nearby. And some of the results that we have, unfortunately, I cannot speak why, because in US, they put, if we have more than 1.9 micron with the 1 watt continuous wave, that is ITAR, and we cannot publish. But I can, why? Because everything I did before, ideas come from myself, my group, so we do. But the new result, I cannot speak with you, but that is exactly as you can see. So I am not going more to the laser part, because that they are the things that you can go again to see. That all of this result that you can see is the unique and is very important. As an example, I will tell you, for all of the gas that we have like TNT and all of the explosive, they have the absorption between 6 to 10 micron. So the Homeland Security wanted to have one system that can have one very fast to have the tune from the different wavelength, and that is exactly that. It was the 3 group, it was the group of the Harvard, Federico Paso, and at the same time Kumar Patel, and at the same time my group. And as you can see, they put that Northwestern University is the only one from the 3 to develop the laser as is contracted. And it was the first time that Homeland Security was coming to Northwestern, because never did they go to university. And that, here exactly the result that you can see, but you can find anybody that is interested, go to our website because it's published. I'm not going to give, only to show you one of the most important as an example for the telecommunication, for at the same time the moving fast communication, they need that photonic integrated circuit, and that is exactly the result that we have. And I would like to give you here, if okay, because I believe that you are not using my, okay. So as you can see, that is this one-dimensional, that now we have the 2-dimensional at the same time, monolithic at the same time, integration with that is unique, but is future again, because everybody needs that. Now, it's only that this result that you can see, okay, the world can work 10 years, 20 years, if they can repeat this result. That is the phase locked and the continuous wave at the same time for the 8.2 micron. So all of that, you can find the publication on that, not just the new result. We put now everything on silicon substrate. That is the world's highest power, 14 watts to put the quantum cascade on silicon substrate on gallium arsenide for the 5.25. That is just published, that you can find that. And again, this one is for 10.8 micron, again, world highest power for that. And the new one that we have now, the high power continuous wave at the same time, all of that is coming one after each other. So only I would talk. I'm going very fast now for the terahertz, because it's very, very important for the terahertz again. That is, we develop, and all of this result that you can see is the unique and is the future. At the present time, I have the contract from the NSA, but we're working on that. An objective is, if any group, any person can have the room temperature terahertz laser diodes with one microwatt, not microwatt, no, milliwatt, sorry, microwatt we did that. 1 milliwatt continuous wave operation, 100% Nobel Prize is behind of that. Okay, and at the same time, frequency comb again, the Nobel Prize. I'm not going today. Just what we did, we came with a very interesting ideas. using double frequency generation to make the terahertz frequency comb. Room temperature terahertz frequency comb, and that is again, this result again is in the Nature Communication, so you can find that. But you are going to say that, all right, what is the, at the same time, how at 100 degrees C, with 1 watt continuous wave, the AR coating, HR coating, no degradation. That is it. So now only in conclusion, in the red that you can see everything, timeline for the first and everything that you can see, or the first or the highest, and that is the mean. And I encourage again all of you that it was the past, present, and the future. Now very fast to go to the T5 semiconductor, not the detector, because I know that most of you are interested on the detector. What is the objective of the detector? We would like really to mimic the nature. Our eyes, you have to know that, is the single photon detector. That is, we can detect single photon with eyes. And at the same time, the artificial eyes, focal plenaries that we do, is that. Now coming, we have photoconductor, we have photovoltaic. We try to create, again, to come with the me up. So exactly as you can see here, in my group, we developed, because when I went to Northwestern, my fascination was for artificial eyes, because it's very hard. Nobody can, especially at university. And that, here we did from deep UV up to terahertz, all of that, and all of that is published in my, I have the book for each of them. And that you can see quantum dots, that now you are working on that, and quantum dots are the, why quantum dots is important. I'm not going to the detail, but that is the things that we did again with the indiophosphide, and that is the problem. Look at that. You have here quantum well-infrared detector, quantum dots infrared photodetector, and quantum dots in the detector, focal plenaries. But all of that is the problem is the following. They are the narrowband. But some of you, if you know that mercury cadmium telluride, that is the one that it is, and is going is the 2,6, that is mercury cadmium telluride, has the broadband. So what indium astronaut, indium antimonade, top 2 lattice, that is developed, proposed by Leo Ezaki, Nobel Prize at IBM, but everybody, exactly as you can see, that is the 3,5 indium antimonade base, and that is the 2,6. Here is the binary of the aluminum antimonade, gallium antimonade, indium. We have all of that from the very high energy up to very low energy, and that we have the substrate gallium antimonade. That is the mercury cadmium telluride that you can see, and that is interesting, because there is no substrate for that. And that, many, I would like only for those that they are expert for the detector and they understand what that means. Here there is one detector of the 14 micron made by top 235 and one with the mercury cadmium telluride. At here between temperature at 20 degree up to 100 degree K. At 20 K, you can see that both of them, they have the same wavelength, approximately 40 micron. When we increase the temperature, mercury cadmium telluride change, go up 20 micron, but the top 2 doesn't change. You have to understand what that means, the physics of that. Anybody has the question that. So what we developed, we did the ETBM theory, and with that exactly, that is the first brilliant zone at the center, as you can see, by changing one monolayer, by doing the gallium antimonade, indium astronaut, superlattice, one monolayer of the one or the other, you can see that we can go from the here, as an example, any wavelength that I want, I can put that here and to simulate and to say that exactly what is the condition I put in my MBE, and that is the world first again, because everybody was working, and that, when Nobel Prize giving something, but nobody could make the focal plenaries, they came in my group, and we did that in 2003, exactly as you can see, mid wavelength, long wavelength, And now I'm going now much faster here to see that how we can go now to the short wavelength. Look at that here by ETBM theory, by to put it 1 2 monolayer of aluminum antimonide, we can change the gap, and in this case, exactly we can do that again, the 2 color, and that. 1971, ideas came from Leozaki. All of the group was working. In my group, we started with the detector and the first the focal plenaries, and exactly as you can see, everything is continued. And there is a article for 5 minutes on the website of the security. You can read. My name is okay. And that we did at the same time. That's the word first, the detector, and after the camera that we did. And this camera, it becomes now a kind of, and everybody tried to work. And now it's replaced in the space station. Now they are using in the space station, as you can see, not the top 2. And just last week I had the Morzi Jablavo. He was one of the invited in my meeting that he explained that. So now for the exactly, yes, one of the important things here is the following. With the top 2, when you have gallium antimonide, indium astronaut, unfortunately, the interface has a problem that I'm not going to the detail. So, and it's very hard for the MBE. So what we did this system. Exactly indium astronaut antimonide. With that you have not, is the gallium free. And that with that we developed, and exactly as you can see here, and we came by the atomic and gap engineering, even to go to the 3 pressure, and the result just again is coming, and that is the timeline of that. So I would like to go to say that what is the future? The future, again, fundamentally, nature is in quantum. When you go to the biology, you understand that everything is the scale of the molecule, okay, the DNA. So we need to come. So the science is progressing, we understand, but unfortunately, the fabrication is something else. So now, at the same time, the carbon, so by that, I would like to say that it was the 20th century, and that is the 21st century. That's the things we do. And the 2 tanks, all of the program manager at the difference, and at the same time, the student, the postdoc, and that Northwestern and Central Research Lab that I learned semiconductor there. So thank you very much again. Okay.
Thank you very much, Professor Razeki, for this wonderful overview of your work and achievements. And I'm sure that you'll be the one to receive the coveted Nobel Prize soon.
But I will explain to you. Nobel Prize is the scientific carrot. What does mean Nobel Prize? Because if you come to my office to visit, you can see that the board, more than 12, 15 Nobel Prize, they visited. I invited them in my conference, and I did a congratulation. Why? I said, you are going to have the Nobel Prize. And they got that. Claude Tanuji, that I know that all of you know who is Claude Tanuji. His book of the quantum mechanics. And he visited my lab when he came from the airport he came, up to midnight he visited. And I said that again, congratulations, he said. But what is the difference? Because all of them, they are my friend, and I see, what is the difference between? They are curious, and they have a passion to understand the detail. Most of us, when we have the problem, what we do? Okay, we change the subject, we go somewhere else to do something immediately. But the Nobel Prize winner, they are those that they don't care about the job, about the money, about anything. They focus to have that. I want that all of you see that for the Benjamin Franklin, I gave 5 minutes talk. Yes, and they try to put that just on is in the YouTube that they are going. And you see that I'm telling, my gosh, don't kill me. Let me to see the result before to die. And that is that. Because this kind of things that you can see, the emissivity challenge, when I did this material, you cannot imagine for the normal people, it was the black magic. But I didn't care, and I had at the same time for you the 3 children responsibility, because you are saying that. I said that 1 hour I didn't miss from class, and 1 hour from my duty as a mother. So you have to understand there is no excuse, especially for the women. So they said that nothing. So that Nobel Prize is the curiosity. And I want that because really, human gave us so much potential. When you use it, but you have to be able to use it. And that is that. So yes, there are so much problem at the same time every day.
I'm sure there will be lots of questions for this interesting talk, but as we are already running late, we'll just take two. One or two questions.
Yes, ladies first. I love
first.
Okay, please.
Madam, thank you very much for a wonderful talk. In fact, I've heard you sometime in IWPST, International Conference on Physics of Semiconductor Devices. You were the plenary speaker there. So it's wonderful to hear you again. And it's just one question, because you mentioned gallium oxide, and there are so many doubts that are being risen for gallium oxide, because it, as you said, it is better than silicon carbide or gallium nitride for high power devices. But then the only negative it has is the poor thermal conductivity. And therefore, people are kind of dropping it for using it for high powered applications. I would just want to know what you think is the right direction. Should one continue to work on gallium oxide as a bulk substrate and then grow epi and go for power devices, or look at only the thin film growth on alternate substrates which have a better thermal conductivity?
Thanks a lot for the very important question that you are asking. Because we had the Air Force, we have a meeting that Ali Said at the same time is the program manager. We had May 20, we had in Washington exactly for gallium oxide the meeting. And it was the best scientists around the world, and especially in the United States, working on that. You have to know that still the gallium oxide substrate that they are using, if you use, because they gave me, because the Japanese they are doing, and that is selling, and the US at the same time, and the German people at the same time, it's a huge activity at the same, and they send me the substrate. I bought that with the different orientation. When you see the substrate, if you do the characterization, especially photoluminescence, you see that huge defect-related photoluminescence, similar to the gallium nitride, gallium aluminum nitride, and similar to the nitrogen vacancy of diamond. All of that you can see. First, they have to solve this problem. They are using the substrate, and at the same time, some of the, similar to all of the different technology that they are doing at the present time, a lot of defect. So that has to be solved first. And that it was the way that I did for aluminum nitride, gallium aluminum nitride, everything that you can see. When I was speaking 20 years ago in all of the meeting as a plenary, especially in the physics department, and I was speaking about the problem. They were telling in gallium nitride, aluminum nitride, this yellow is related to the carbon and oxygen. I was telling no, after my experience, it was related to gallium vacancy. It took 3-4 years after that. One of my program managers, the Max Yoder, called me, "Manager, you were right, because the theory showed that you were right." I said, of course that I'm right. So that is very important. But we have to understand first the defect, and after that for the phase transition. If some of you to look, because my PhD, it sounds like it was perovskite, the lead phosphide, similar to the gallium oxide, with the different phases. So that is different phase, and each phase has a lot of application, not only for the high power transistor. You cannot imagine how rich it is, but it takes time. Many groups they are working, many excellent groups they are working. After 50 years, it was the first time I demonstrated the kappa and beta phase transition. Why? Because with the background that I had with that, and that it becomes now everybody, and especially in the government laboratories in US because they believe that they are God and the other. Now, to show to them and say, so answer to your question, I want really to encourage you and all of the scientists that are, because that is very important subject. There are many that are working on the oxide, indium oxide, copper oxide, iron oxide, and we are going to have in this meeting at this time. But the gallium oxide is unique because it's the direct gap, semiconductor, 5 electron volt, and you can do with the aluminum and with the indium, and to have the composition and to tune, and the beautiful. So that is a lot. So answer to your question, yes, my dear. We need to work on that to understand the problem, yes.
So the rest of the questions, we'll carry them to the coffee room. With that, we'd like to thank, if I may say, the Madonna of MOCVD. Thank you very much.
Thank you very much. But again, I would like to encourage all of you, any of you, that you have any question, I encourage you, go to our website, because any subject that you can see, you said that now is more than 1,500 publications and more than 1,500 plenary and invited everywhere. But most of them is on the website. And please go to just last year in the SPIE, I didn't go for my talk, and I sent for the recorded one, for the 30 minutes. For the top 2, more than 1,000 heat is then only for that. So look at that, any question that you have, exactly, I am really happy to discuss. And most important part, I am always looking for the genius student and postdoc. So welcome to Northwestern Security to work with me for the next generation of the Nobel Prize.
Thank you so much, Professor Razegi. I now request Professor MSR to hand over a memento on our behalf.
Excuse me?
This is a small memento from our department.
Perfect. All right. But that is more has to be for Professor Somnath. You give him, because he is very, very persuasive, and to be able to bring me here, by the way. And it was a great pleasure.
The thanks goes to everyone.
Thanks again. Thanks for everybody. Thank you.
I also request memento for Director in Charge, Professor Vasa.
Okay. So. Not to you. I can give it that to you, but for your talk.
Lakshminarayan, Head Department of Physics. So as you know, we are running about half an hour late, but we will not cut down on your well-deserved tea time. So let's afford to have some late in a conference, otherwise what is the conference? So we will meet at 11:30 in the respective halls. One of the sessions, the solar energy material session, will continue here, that is the TTJ auditorium. Then the other session on thin film will be in the hall 1, and then the third session is on hall 3, which is just around. So please enjoy your tea and yeah, another request, the next session, the PowerPoint presentation by the invited speakers, the volunteers are available in the respective hall. So we request you to please hand over your presentation.